All right, welcome back. We'll be kicking off the first project this week. Just have to talk about the parsing side of the equation and how it joins with the scanning side. Any questions before I dive into all that? All right, so let's see. Let's quickly reprise what we were doing last time. Oh, right. So we're looking at the scanner. We had this option came up due to that the scanner by default generates code assuming that your source of input to be scanned will come from multiple locations, and YY-wrap is a function that facilitates that. We don't have that need, so we suppress the generation of that code with that flex directive. And then YYLex is the name of the function that the code generated produces that actually does the scanning of the input stream and identifying tokens from a set of regular expressions that you come up with. And then, let me see, I think I put that today because I didn't get it in writing. Yeah, so a couple takeaways from last time was that it is certainly possible that you'll have expressions in here, more than one expression will match whatever the stream of text is coming in. If that's the case, it'll take the larger match. And if they're exactly the same size, it will take the first match that it encountered. So extending that then to how you're going to want to structure these regular expressions is things that are very specific, like this hard-coded INT, you're going to want earlier in the list, and then expressions that are more general would be further down in the list. And as far as languages are concerned, then that would be like our keywords would all appear before we would have a regular expression to find all doubles, for instance. All right. So there's that. Let me see. I think that's all. Yeah, that's all that has in it. So today, then, we're going to talk about Bison, the parsing side. And it's in Bison where we describe a grammar and try and determine whether that input that we're getting matches the grammar that we've designed. So I've got some, oops, in the wrong place. All right, so to start here, when you're describing a grammar, you describe it in terms of tokens. And there are two types of tokens, either a terminal token or a non-terminal token. A terminal token is something that comes from the scanner. It's found a string, it matches, and whatever that regular expression match was, that then would be a token that is sent to the grammar. Non-terminal tokens, we'll look at this just a second down, a little bit lower in this file, is that we describe a set of rules for describing a grammar, and those rules culminate in non-terminal tokens. So let me actually just jump immediately to this example here. Lines 11 through 21 constitute a grammar. And for convenience sake, all of the words in uppercase are terminals. So these would be things that would come from your regular expression engine from the scanner. And anything that is lowercase would be a non-terminal token. So what this is showing is that if you receive a preposition followed by a definite article, followed by an adjective, followed by a noun from your scanner, then that will, the term we'd use is reduce to this non-terminal token. Okay. You'll note, and so what this is, this whole thing is referred to as a production, and it is a rule or a set of rules that will reduce to the non-terminal on the left. So the syntax shown here is you have your non-terminal, then a colon, and then a list basically of an ordering of the terminal tokens. This whole thing would be a rule. You can have more than one rule, and there are a couple ways of specifying more than one rule. I think I've got that here. So this is showing that there are 3 rules here, and they're separated by the pipe, which of course corresponds to or that we know and love. So an adjective list can be either an adjective or 2 of them or 3 of them. Note that an equivalent way of structuring the grammar is what's shown at the very bottom of the screen there, which I can have these as completely separate productions. So again, this whole thing I would call a production. Basically anything, a non-terminal followed by a colon, followed by 1 or more rules. This whole thing taken as a whole is a production. Okay? So this is 1 production, this is 3 productions. These 3 productions are identical to this production here. You can do it whichever way you want. Folks tend to do it this way, but you do have the flexibility of dividing that up this way. The reason that this is called a production, and then let me, this production has 3 rules. So sometimes I'll say production, sometimes I'll say rule or production rule. When I say production rule, I'm referring to one of these 3 things here. The whole thing taken together would be a production. The reason the word production is used is because in language theory, these grammars describe all of the legal instances of the language that you can generate. So, for instance, what this is doing is, and in fact, I can get rid of this temporarily. We'll come back to that some other point. Let me take lines 31 through 33 and move them up to 15. All right. So this grammar that spans from lines 11 through 22 describe all of the sentences I can generate. And so the idea is that this can generate these 2, and then this can generate this, and then note that this can be generated one of these 3 ways. So that's why these are called productions. It's because it's what the non-terminal produces. However, we're coming at it from the opposite direction, which is we're not interested in generating all possible C++ programs, or in our case GPL, all possible GPL programs. What we're interested in doing is being given something and answering the question, is this legitimately part of the GPL language? And that's what we're doing when we're compiling C++, is these rules are being matched to finally determine whether or not you have a valid C++ program. And if you don't, you get errors and nothing happens. And if you do, it's able to take some action and, in our case, translate down to an executable that we can run. Okay? And in GPL, it would be ultimately something that we can interpret and run. So, again, the terminals are the things that you get from the scanner. So you will never have a non-terminal on the left-hand side of these rules. The terminals will only appear on the right-hand side of the rule. Note, of course, that non-terminals can appear on, excuse me, I should say production, not rule. The non-terminals can appear on the right-hand side as well, and that's just showing that if all these come from the scanner, so we'd need an example. I guess that's why I had the quick brown fox stuff. So if I wanted to find out if this is legal in the language, then what would be happening is over the lazy dog would match this over the lazy dog. That whole thing would reduce to an object, and then is there a verb that precedes our object? Yes, jumped. And then that then reduces to a predicate. And here we have predicate and subject, so now we have to see, do we have a legal subject? And then we have noun, adjective, list, and definite article. And sure enough, there's our noun. This adjective list matches here. The adjective becomes an adjective list, and then the definite article. So this whole thing does ultimately reduce up to being a sentence, and it's legal in the language. Okay. You'll see different nomenclature for this. Sometimes you'll see 2 colons, or you'll see something like an arrow or something like that. The Bison file that we create actually takes a colon, so it's convenient to write things that way. And in fact, you can get on the web, and here's a grammar for the C language, and you can see that they follow a similar thing. You have your non-terminal, a colon, and then separated by this pipe or a set of rules. This is a nomenclature simplification. That would be a terminal token, the comma, terminal token. And rather than writing the word comma or some equivalent, they just show what that terminal actually is that was encountered by the scanner. Okay. So with that, let's go ahead and try building our first parser. So the Flex had a file with a -L extension, or a .L extension. Bison is going to be a .Y, and the reason for Y is because the predecessor to Bison was Yak, so it was a Yak file that you were creating. So we'll go ahead and create first Bison .Y. Now one of the nice things is that the syntax roughly approximates what we had for our Flex file, which is we have 3 sections with a pair of parentheses or a pair of percent signs separating each section. And just like in the Flex side, we have directives as in the first portion, all of the rules in the middle, and then anything after the second pair of percent signs is blindly copied into the generated code. So let's go ahead and create a rule. We'll call this verbiage. And again, it's not a syntactic requirement. This is just for visual clarity with the uppercase and lowercase. So I'm using uppercase to represent any sort of terminal token. Following each rule, so this is the rule, I can have an action. And it either goes all on the same line here. In general, you're going to want it on multiple lines, so it is not unusual to see the curly braces used. And then if it's really long, and we'll find when we get into the projects that these can be over a page of code sitting here for this rule. So you do have the freedom to format this. I'm going quite simple, so I'm just going to say this is horribly incomplete, but we can go ahead and try generating the code and start sifting through the errors that we're getting when we do this. So let me leave that there. Let me come over here. Let me get into Linux. Bison. First bison.y. All right. So first we have to say, provide information saying that this is in fact a token, a terminal token. And we do that up here where we provide directives, and it's actually called token. And we just say, this is going to be a token that we're going to receive from our scanner. That should get us past the first issue. Okay, that actually generated the code just fine. It knows that it's a token and that there's a rule there that if it encounters that token, it will reduce to that non-terminal token verbiage. If we look at the files that were generated, whoops, let me do it this way. We have this right here. The parser generates parsing tables. That's why the tab abbreviation, that's for tables. And it's a C file that's generated, so we can go ahead and compile that. And in fact, what I'll do is I will add to this the same thing that we did for the last one. Is use a little short circuit logic at the shell here to have the compiler run immediately after successfully generating the code. So I do that. There are going to be errors that I can't see. All right. So yylex, if you recall, is the function that is generated by our scanner, by Flex that we did last week. And it's just simply saying it isn't declared. So we can solve that problem by providing a function prototype to it. So I'll come back up here, and we have the same idea that we had with Flex, where we can either indent to get code, or we can kind of bracket it with these curly directives, and then we are free to stick in code however we like. I like this. If for no other reason, the syntax highlighting seems to, in my editor, seems to do a better job if it's seen those. So here we'll go ahead and say we just have to know that yylex doesn't take any arguments and it returns an integer. We'll go ahead and give that a go. Do it all again. Okay, now we got some mundane stuff. Doesn't know about cout. We can certainly fix that. So let's go ahead and include, oops, we'll put it up here in our code. Include IOStream. And we'll put a using directive. Give that a try. Now what do we have going on? Oops. Okay, so error is the function that the parser calls when something goes wrong. And you'll see there are a couple errors that the generated code will handle. The first is probably the most common, particularly if you're a 111 student. And it's error in syntax simply means that, I guess this is the better one to look at. This grammar describes everything that's legal in the C language. If a token is passed to the parser, right, the parser's been defined by all these grammar rules. If the scanner passes a token to the parser and it's unable to match any of these rules in the grammar, then that is an error in syntax. And that makes sense. If you create a program that's just simply the word int twice, you're going to get a syntax error because there is no grammar rule that has the keyword int 2 times in a row. The second error was memory exhausted, and let's hope we never write some monstrosity that it's absolutely so huge that you exhaust the memory on your computer. All right. But ultimately, this error is saying it doesn't know where this function is, and that is because we are writing the scanner. We have to write the function that handles errors and reports them. And this topic will come up again as we dive into the projects, because dealing with errors is more than just simply saying, I have an error. There's error recovery, right? So the idea being when you're compiling your program, if you have some sort of error, the variable isn't declared, or an error in syntax or something like that, the compiler doesn't just stop. It actually tries to recover and continue parsing. And so that's a topic that we'll return to on how we can get error recovery. Right now, we're just interested in creating a simple YY error function. I could put it up here, but I like the idea of maybe having the prototypes up here and then actually sticking the code down in this last third here. So the prototype for the function is going to be, it doesn't return anything, it's YY error, and it is going to take a C-style string that has the text of the error. Go ahead and jump down here to the lower third. Whoops. Add a set of curly braces, and then whatever we want to do. And all we're going to do is we're going to say ouch. I'll write that to C error, and that means I should come up here and go ahead and add another using statement. So let me go ahead and try that. And now, all right. We have to write a main function. We haven't written a main function. So when we first looked at the scanner, we had this idea of it going through and it finding all the tokens. From the perspective of the scanner and parser together, it is the parser that's running the show. It is the parser that's interested in finding out whether this stream of tokens is a valid grammar or not. So the parser, whenever it's ready, is going to actually request another token from the scanner. And what we had before is the scanner just ran endlessly, consuming this stream of text, and we'd get kind of stuff printed along the way as it matched various regular expressions. Now we need to make it so that the scanner, as soon as it finds a proper token, it just simply returns it back to the parser. So starting out, again, we need to deal with main. So this is a linker error, so we need to write a main function. Note that I haven't even looked at a scanner yet, other than what we did last time, so we'll have to go ahead and insert that. And we'll look at that in just a moment. So we have to write a main function. And, whoops, I'm sorry, I need to come back here. Same deal, we'll come down here to the bottom third. And we'll just have this main function call the Bison generated function, YY_parse, and it is this one, this function, that is going to try and run the show and repeatedly call YY_lex. We can look at the generated code real quick. Let me go ahead and, whoops, let me leave that up. Let me come down here. I run this, and I'll still have the linker error. Note that I don't have any issue with main being undefined. Now I have an issue with a linker error with YY_lex being undefined. And this makes sense. So the parser is calling YY_lex, it's calling the scanner, but of course I haven't put any code on the compile line here that would have been generated by the scanner. Right? It's a scanner that defines YY_lex. So first, just to show it, oops. So there's a prototype to the function that this generates. Here is actually the source to that function, and this is going to be a nightmare to look at, as generated code usually is. But if I look for YY_lex, so this is still inside that function, and we probably aren't going to see a nice, tidy little while loop, but it's essentially the equivalent of a while loop. What's happening, again, this is all inside of YY_parse, that function. YY_parse is probably using this label as its loop. So you see the dreaded goto. When I was learning programming, everyone said how bad a goto was. Now, nobody even knows what a goto is anymore. But that's being used here. So it's probably either looping on YY backup or probably higher up is YY default, and we're getting a loop, and it's calling this line of code repeatedly. So we've got everything we need, except we need the code for YY_lex. So let's go ahead and write a scanner. What was I called this first Bison. I'll go ahead and call it first Bison. Give it the same name, but of course it'll be a .l. It starts out the, hang on, let me do it this way. Leave that alone. Let me go first Bison .l. So this is going to be our scanner. And quickly, what we're expecting is the only possible thing we can get from the scanner is this token that I've called letter. So hold on to your hats. There we go. That regular expression will match a letter. And when I match a letter, the action I'm going to take is to return that terminal token. So now you see the difference in YY_lex. When we were dealing with YY_lex, and I'm repeating myself a little bit, when we were dealing with YY_lex on Thursday, in fact, we should just look at Thursday's code real quick. We just simply called, we had our main function and it called YY_lex. And, oh, I don't have anything here, but then we had our expressions here and it just printed something out, which means it found a token, printed something out, kept going, found another token, printed something out, kept going. Now that's changed, where as soon as we find a token, we want to return back to the parser saying, hey, we found this token, and now the parser is going to try and match it to its grammar. Okay? This is going to be incomplete, but let's go ahead and run with it. So here I'll say, I'm going to actually enhance my line here. So we want to say flex first bison.l and bison first bison.y. I should probably reverse those, but maybe yeah, I will reverse that. I actually want to generate code for the parser first, and the reason will become clear. in a few moments. All right, so I generate code for the parser, I generate code for the scanner, and then I'm going to compile them all. I don't have it here yet. That is going to be, anyone remember what the generated file is called for Flex? Yeah, that's it. lex.yy.c, right? So now I've got both of those. I'm sorry, that's low down. Let me pull that up a little bit. There you go. So now I've got both .c files here on the G++ line, the file that generated by Bison and the file generated by Flex. But I won't get that far because I think I'm going to have problems. I think I'll get through Bison okay. I think I will crap out on the Flex line. Let's find out. Let me zoom in here. Yep. So the .l, it's a complaint. It doesn't know what letter is. What the hell is letter? So on the Bison side, we described what the terminal tokens are. In our case, there's just one. Right here. Whoops. No, I'm in the wrong place. Right here. That's the directive. It's in the upper third here that says that letter is one of the terminal tokens that the scanner generates. But the scanner doesn't know anything about that. So we need some way of this information here getting to the scanner. And the way you do that is by adding an option to Bison, which is -d. So let me do it by itself. So if you add the -d option, then if I look at my files, there is another file that has now been generated, and that is a header file. And this header file contains the information on the terminal tokens. We can actually go ahead and look at that. We called it letter, first bison.tab.h. Oops, there it was. So in your Bison file, when you describe terminal tokens, it adds an entry to this enumeration. So that means anywhere that we use letter as an identifier, it is going to internally ultimately convert it to 258. So now when we look at this, it's returning 258 back to the parser, right? And anywhere we refer to letter on the parsing side, it matches up. So that's how we go ahead and connect the two. Let's see. Okay. That means that, what do I need to put here, though? Yeah, include the header file. So I can either indent it, or again, I'm preferential to that. So now letter is defined in the scanner. Let me try running the scanner by itself, see if that did fine without complaining. So now let me find my big chain here. I run Bison, then I run Flex, and then I compile it all, assuming that I reach that successfully.
You have the -d.
I don't have the -d, thank you. I had it when I was isolating it, so I add the -d. I didn't write my changes. YY wrap. What's my solution to that problem? Again, I'm in the flex file, the .l file. We do not need our scanner to be wrapping multiple inputs. And victory is ours. Yes?
What was the command to generate the .tab.h file again?
You put this -d option for Bison. All right, so let's look at our scanner. I'll look at it over here. This is our scanner. Whenever it encounters a letter, we get letter as a terminal token. Looking at our parser, our grammar says it will take a letter, and when it encounters a letter, it will run the action that I've described, and then it will do a reduction to this non-terminal token. That's my grammar. So let's find out what's legal in the language that we described. Printf, how about the letter T? And we will pipe that into the executable that I created. I'll just go ahead and zoom in here. How about, what if I do a second letter? I'll choose a different letter, doesn't matter. What's going on here?
There's no production for two letters next to each other?
Right. The only thing legal in this language I've described is to have the letter. That's it. That's the language. You can give me 26 uppercase letters, 26 lowercase letters. What's that, 52? There are 52 possibilities for my language, and that's it. So we could do this. We could say we have another rule. And I'll borrow this. That should work. But of course, we immediately see the issue here, which is it doesn't handle 3 letters. What happens if we do, anyone want to guess what will happen if we do 3 letters? So it did actually match one rule, and then after that, it got a 3rd letter token, and that was an error in syntax. There's nothing in the grammar that allows us to support the 3rd letter. So there's actually a strategy that we can use. Oops. Come back here. Recursion. Now it's incomplete. It's not done yet. So what I have is necessary but insufficient. So let's look at it in the middle of it, right? The problem is kind of kicking this thing off. But if we start in the middle of the whole thing, I've got a bunch of verbiage. Letters have been coming to me and I have verbiage. What happens if I get another letter? Well, I've already got verbiage. So if I've already got verbiage and the scanner sends me another letter, do I have a rule that can handle that? Yes, absolutely. It matches the rule on line 14, does whatever the action is, and then reduces down to verbiage. And then I get another letter. And that'll also match line 14, and it'll reduce down to verbiage. And if I get another letter, then it'll reduce, yeah? This starts to throw some people a little bit about visualizing this and imagining what's happening. And I think what's instructive is to go back to this. So I can this, let me see, where do I have it? I put it lower down, I think. Yeah, right here. Oops, did I do that on the other one? And so this is where we have this chain is quick, brown, joyous. So quick reduces to adjective list. Now I've got an adjective list. I suddenly get an adjective. Oh, I've got a rule to handle that because I already have an adjective list and an adjective. So my quick had reduced to adjective list here. And then the next thing I get is an adjective, so that'll reduce. So quick, brown reduces to adjective list. And when joyous comes, joyous would be here, and this rule would have been what was the reduction from quick and brown. In fact, probably the best way of thinking about it is with a stack, because a stack is actually how this stuff gets implemented. Is if I have quick, brown, joyous, and if this period represents the top of my stack and everything to the right of it is stuff that we haven't seen yet from the scanner, and so the scanner says YYLEX, it returns an adjective. So now the scanner has this adjective, and I ask you the question, is there a rule where an adjective that matches an adjective? And yes, it's on line 31. So what the parser does is it does that reduction. And then the parser says to the scanner, YYLEX, give me another token. And it returns another adjective, brown. And then the parser goes, do I have anything that matches adjective list and adjective? Yes, I've got that on line 30. Okay, I do whatever action I have. You're not required to have an action, but if you do, it does whatever action you have. And then it reduces. So whatever matched that, where was I? Here, adjective list in brown matches line 30 and ultimately reduces to adjective list. Parser says, okay, I'm ready to continue. Give me another token, YYLEX. It gets back joyous. And same thing, line 30 does match. So that whole thing reduces to adjective list. And then it gets the next thing. Maybe it's jumped. And we have, I hope we have, no, I don't think verb object. All right, so I jumped in the middle of this, but then ultimately it'll try and find where that matches the grammar. And if it finds an adjective list followed by a verb, then it'll match and reduce, or maybe it needs an additional token before it can reduce, and it'll ask for another token, and it may get 2 or 3 tokens before it's able to match one of these rules, and then a reduction can occur. So this process is simply for the parser to determine whether you have provided a legal language for the grammar defined. Let me see, do I? Yeah. All right, shift reduce. Let me take a look at what I got there. Probably, yep, I've got this stuff. Let me get rid of that. We'll be talking about that more in the days ahead. And there we go. So I should, whoops, I got to go up here. Let me rewrite this. This is misleading. Yeah.
I think I missed part of the first Bison.y file because I see it's 26 lines. Oh, wow.
Guess I ought to do this, eat up fewer lines. I think more people do this than do this. I'm just a slave to having learned the language and worked in software shops that did that early on. So that gives me the creeps a little bit, but I understand that's the way you all roll, so I'll do that for you. Takes up fewer lines. Questions, comments? Let me go ahead and enhance the grammar a little bit by considering other tokens. So let me actually throw it to you. You all guide me through it. I want to have an additional terminal called number. And that can roll into verbiage as well. So what are all the steps? What do I need to do to make that happen? Yep. So add another token. Call this number. Or how about, yeah, the number's fine. All right. Regular expression in the scanner. Okay?
That's a digit.
Say that again?
That's like a digit.
Yeah, I'm saying number instead of digit. That's fine. I'll change it to digit. I know that.
It's not required.
Oh, sorry, yeah. Say what to do with that token, whatever action you're going to do. We want to do like verbiage and digits together.
Oops. I'll steal that output. Got a digit. Going to reduce to non-terminal verbiage. So recall that I can either do it this way or I can go ahead and use the pipe to say that that's another rule for verbiage. Both of those are perfectly fine. I'll go ahead and do this. Let's take a look. All right, so that was the original. Let me clear the screen. Let me throw a number in there. Did I change, have verbiage? Yeah, I got it. Yes?
Do we treat constants differently, or like how do we treat constants differently?
So that's an interesting question. So you're thinking like a literal 23? You mean in the in like GPL or something? What do you mean constant?
Like an int constant. Do we draw distinctions between constant elements and non-constant elements, mutable elements?
Well, how you treat it is a function of the grammar, not. It'd be in the action, all the stuff I have in curly braces, right? You would certainly have. Let me go here. So this grammar. Where's my constant expression? So here's the const qualifier. They have type qualifier. That's going to reduce up until you have something that is type qualifier. It looks like that deals with pointer. We're going to see it in several places here. And then you have declaration specifiers. So a declaration specifier is going to be like int, const, int. So you see that it would be like something you would do in the action. If you got const int x, and then there would be an identifier. My guess is if we go to the declaration specifier, there's an initialization list. You're eventually going to be able to piecemeal this thing together in the grammar until you have a constant expression. And so it'll be legal grammar, but all the magic is going to happen with the action that you take when you find these various, right? So when you finally hit that line in the grammar where you know that constant x equals 5, wherever x is used, you want to put a 5, there's going to be some sort of action taken under the hood to make note of that. Mm-hmm. There is an alternative way of expressing this. And that is, we can, if we want, we can jettison, how do I want to do this? Something like that. Nope, I did it the wrong way. Let me do it this way. All right. So this is our startup conundrum. And as an alternative to specifying each of these individually, you can, and I heard it said, have an empty rule, which means that having absolutely nothing will match verbiage. The empty rule is specified by literally having nothing there. So if I had some sort of non-terminal here, there's the empty rule. Okay? It is very visually easy to miss or misinterpret. So Bison provides a directive that does absolutely nothing. It's just a visual cue so that you know that there's an absence of any token there, and that is a rule, the empty rule. So let's first, what am I hitting to do that? Oh, I should add it. Let me add an action that we take. Hello. So let me try that. So let's look at how that works and why that works. If this is my input 23AB, the parser calls yylex. Yylex gives it back digit. And the parser looks at all of the grammar rules that it has. So note that when the parser is trying to match, at this point it's just looking at all the rules, right? It isn't looking at what the reduction is, because the reduction isn't important unless it finds a match. So it looks at all the rules, and there are only 3 rules. And those 3 rules are Verbiage letter, well, digit, again, the 3 is waiting to be read in. This is the token it just received. There is no rule here that begins digit. There is no rule here that begins digit. So at this point, it's faced with crapping out, except it does have a rule where absolutely nothing will match. And that's exactly the situation that it's forced into. There's nothing that is going to match at this point. And so it reduces to verbiage. Now, it does have a match for that digit that it read in, where verbiage and digit matches this rule, and it can reduce to verbiage. Yes?
How does that work if there's multiple ones that have empty then? Like, wouldn't it, because it did empty before it even got to the number when you had an instance with just a single number 2. So if you have multiple empties, is it going to trigger all the empties?
Like that?
Or it's just going to trigger the first empty? It's going to take precedence, right? Always? Yeah, like would the another ever...
So you get all sorts of complaints because it's ambiguous.
But if another also went to something as well, an empty was just like a secondary alphabet, like, doesn't it break down when we have 2 things with an empty?
Yeah, it's a conflict.
Okay.
I guess you could do it like this.
But
There you go. You get these either shift reduce or reduce conflicts, which we'll be looking at in some detail in the days ahead. In short, shift means to ask the scanner for another token. Reduce means that you have a match and you can go ahead and do the reduction to the non-terminal. And so this is saying that there's a conflict because there's more than one possibility, an ambiguity. And in this case, this could either reduce to verbiage or this could reduce to verbiage. So that's the issue you have here. So the grammar, ultimately the grammar has to be unambiguous. All right, so now our final piece of the puzzle is what we're often interested in is what precisely it was that the scanner scanned. Because we get the token letter or the token digit, but we've lost valuable information, like what was that letter of the alphabet or that digit, right? We might want to actually use that over here. And with that, I think I don't have it open. Let me come here. Oops. All right. So let's see, how can we start interpreting this? So this is a flex file here. And when you run flex, rpn.l in this case, it will generate lex.yy.c. This is the source generated. And then this is showing the complement on the parser side. When you call Bison with the -d option, it's going to generate 2 files, a .c file, and then the header file, which you're going to want to, of course, include over on this side here. there is a couple pieces of information, or I should say variables, that are defined. On the scanner side, there is a variable called YYText. And YYText is a C string containing the contents of the expression that was matched. And we can go ahead and play with that right now. So if I come here to firstbison.l, cout, I found. I'll use like this fancy arrow. And I know that I'm going to need to include IOStream. I know that I'm going to need like a using statement for cout. And I'll do something similar for the digit. Maybe I'll say, whoops, that wasn't good. Put that there. Go ahead and run. All right, so first we get the empty rule, and then it finds the A, and again, this is a scanner, so you can see that YYText contains what expression matched, what the specific stream was that matched that regular expression. So the next thing we need to do is we need to get it over onto the parser side. And the parser is, it's going to be this YYLVal variable. And YYLVal is, if you don't do anything with it unadorned, it is simply just going to be an integer. Okay? For anything other than toy examples, that just simply isn't going to work because, and even in our simple one, we have an integer and we have a character type. Now you could argue that you could store the character in an integer, but we look at RPN, we're going to have multiple types coming, doubles, strings, identifiers. So we need a more complex construct for YYLVal. And that construct is a union. So first, yeah, I'll pick on myself, teacher. And then, let me see if I can do this in a map. So, let me do that. Let me come here. So there should be nothing, hopefully nothing untoward there. Just creating a structure object, creating it, initializing the members, and then printing them out. And there we go, a little bit sloppy on the output. Can fix that on the next edit. If I get the size of it, so let me say size of teacher equals size of teacher. All right. Oh, damn it. What in the hell am I thinking? I did it totally backwards. The size, I got this one right. The size of a teacher is 12, not to be confused with the 0.12 that I poorly chose here. So we have four bytes for the float, 4 bytes for the age. And why did we get 4 bytes for the integer? Or, excuse me, for the character? Just because it's padding it with 3 unused bytes to the next word in the memory layout, so that's why that is. If I make one change, let me do this just so I can. All right, look at how pretty that is. All right, I'll change this to 99, so we don't confuse that any longer. If I just make one word change to this program from struct to union, compile it, run it, and what's happening? What's the difference?
Yeah, a union, it stores all the data types like kind of on top of each other basically. And it uses the same memory for all of them. So when you're changing, I guess GP is the last one you set, it's also overwriting the memory for initial and age.
Right. So repeat it for the sake of the recording, and I know I'm out of time, so I'll finish this in 20 seconds. Rather than memory being set aside for each, there's enough memory set aside for the largest member of these here. And to be sure, I'm initializing that 1 byte to 65 here, but then the 1 byte gets whatever the equivalent of 32 is, and then whatever the internal representation for the float comes after. So this prints out the first byte as if it were a character, but it contains whatever zeros and ones were flipped for 3.99, and a similar issue with age. Yeah. All right. So we will pick it up right here on Thursday.